On this slide, we talk about sheaves. So first we give a motivation. So what we do is we draw a complex plane. And we will denote this complex plane by letter X. So we have a complex plane, and on this complex plane we consider all functions, all complex polynomials. That is polynomials with complex coefficients. So on this plane you have the x-axis, and on the y-axis you have imaginary numbers. So we draw certain sets in this plane X. We have set u1, then we have set u2 which is contained in u1, you have set u3 which is contained in u2, and so on. So we have this big complex plane X, and on this complex plane X we consider polynomials with complex coefficients. So polynomials with complex coefficients. So consider this point P1. This point P1 lies in X, but it is outside set U1. So in set U1 you have the complex polynomials. So on the entire plane you have these complex polynomials. So on set U1 also you have complex polynomials. But in addition to complex polynomials, we can also have fractions like fx divided by gx, where gx could be of the form x minus p1 square or x minus p1 cube, or so on. So we can talk about dividing by x minus p1. So we could not do this outside u1 because this rational function would not make any sense because there is a pole at p1. So similarly you consider a point p2 here which lies in u1 but lies outside u2, and similarly point p3 which lies outside u3 but lies in u2 and u1. So similarly for u2 you can also consider functions of the form fx by gx, where gx is either of the form x minus p1 raised to the power of n or x minus p2 raised to the power of n, because both p1 and p2 lie outside u2. Similarly p1, p2, p3 lie outside u3. So you can consider rational functions here. In addition to polynomials, you can also consider rational functions whose poles are precisely p1, p2, p3. So as we leave out points, we can form a richer set of functions on the smaller set. So on the entire plane you can only talk about polynomials. You cannot talk about rational functions because denominator will have certain poles in the plane since the complex polynomial splits. So when you take smaller and smaller sets, you get a richer set of functions. So consider this increasing sequence of inclusion, u2 in u1, u1 and x. So corresponding to x we had just the polynomials, but when we went to u1 we got not only the polynomials were included but some rational functions also. And when you reach f of null set, you should have all rational functions. In fact, that is so C with the round bracket. So this is what Mumford writes in his book, but Hartshorne writes f of null set as 0, and we will use the second convention. Essentially it should be a final object in the category, but we almost never deal with null set, so we do not have to worry about it. But the point is simple, that in this example on the entire space you have only polynomials, but when you take smaller sets you can talk about rational functions because you can choose as denominator those points which are not in the set, as we have seen for p1, p2, p3. So for u1 you have polynomials plus denominators x minus p1 to the power of n and all other points which are outside u1. Similarly for u2 you have denominators which are all outside U2. So you can have x minus p1, x minus p2 and all other points which are outside U2. So you can see that how we have arrow reversion. Yeah, you have inclusion on left hand side and then you have inclusion on right hand side, but arrows are in the opposite direction. You can do the same thing with continuous functions. Yeah, a function which is continuous on a smaller set might not be in a bigger set. Yeah, on a bigger set it might have non-differentiable points somewhere outside. Similarly, differentiable functions, they might be differentiable on a small set, but on a bigger set they might not be. Similarly for holomorphic functions and so on. So this was a nice space, but sometimes the space is not nice. The space just might consist of like two circles. That is it. So this entire space consists of two sets, say U1 and U2, and none of these sets are contained in each other, and they are disjoint, and both of them contain the entire space. So under such circumstances we do two more conditions, uniqueness and gluing, to make the space into a sheaf, and this will be clear once we write the definition. But this is the general idea of a sheaf. Every time you have something in your mind about sheaf, you should think of this example and think of arrow reversions. Like you have inclusion of spaces on one side and the corresponding rings on the other side have the opposite direction of inclusion. So first we start with the definition of a pre-sheaf. So consider X as a topological space. So a pre-sheaf F of abelian groups on X consists of the following data. So the first one is, you consider U as an open set of X and you associate Fx an abelian group with it. Yeah, just like in our example we had the complex plane and we associated complex polynomials with it. Yeah, so you associate abelian groups. Second is, you have this inclusion map and corresponding to it you will have a arrow reversion in the morphism of abelian groups. So you write this as rho of uv. Yeah, it goes from u to v, so that is why rho of uv. So you have a morphism here. So the inclusion v into u leads to a morphism in the opposite direction. So these two conditions are subject to the following three conditions. So f of null set is 0, this we have mentioned before. So if you have inclusion from u to u, then you will also have a morphism from fu to fu, and that should be ID map. So you have rho u to u as a ID map. So 3 is, you consider another set W which is contained both in V and U. So you consider another set W which is contained both in V and U. So we write down the inclusions like this. W is included in U, but W is also included in V. So this figure would imply that we get the following commutative diagram in morphisms. Yeah, I'm doing nothing, I'm just going to reverse arrows as in point number 2 above. That V is included in U, so you get an arrow from FU to FV, and that is what we are doing here. I'm just reversing arrows. So the inclusion diagram of V, U and W on the left will induce a diagram on the right in terms of group morphisms. So you can find this definition in Hartshorne. So pre-sheaf is a sheaf. Yeah, if for U as an open set with some covering, so U is open set with the covering we have the following two conditions. Yeah, so you, for every set U there is a covering and the following two conditions are satisfied. So number 4 is, say S is an element of the abelian group F of U. So if S is 0 on each part of that covering, so it is 0 on V1, 0 on V2, 0 on V3, so on, then S is 0 on the entire set U. Yeah, so this is called the uniqueness condition. Now why it is called uniqueness? Because see, suppose there are two functions f and g, and f minus g is 0 on each vi. Yeah, so f minus g is 0 on each vi. That means f minus g is 0 on the entire set U, and f minus g is 0 means f equals to g. So that is why it is called uniqueness condition. So if two functions can be identified with each other on each cover or each set of the cover, then they are equal. So condition number 5 is called the gluing condition. So say Si is element of the abelian group FVI. Then for each ij, so if this function agrees on intersection, then you can glue these functions together to construct a global function S. So on the intersection of the covers, the function agrees. Then there is a section or an element of the abelian group Fu, such that when you restrict it to each set, you recover the original function. So basically you are gluing the functions together to get the function on the set U. So we will make a diagram, it will be clear. So let this be set Vi, Vj and Vk, and there is a, we will just write everything clearly. This is Vi, Vj and Vk. So this is Si on Vi, Sj on Vj and Sk on Vk. Yeah, and on the intersection it agrees. So intersections it agrees. Yeah, so it agrees here. So you can write a global section S by gluing them together at the intersections, and obviously when S is restricted to Vi, you get Si. So on this slide we talk about certain examples. So again we will fix a topological space X and take its open sets. Now in the definition we talked about f of u as an abelian group, but we can take f of u as a ring or as a module. So we start by fixing u and X, where X is the topological space and u is an open set of X. And our first example is f of u is continuous functions from open set U to real numbers. Yeah, so this you can achieve by evaluating the function at a point. For example, take x plus 1, you evaluate it at 0, you get 1. Take x minus 1, evaluate at 0, you get minus 1, and so on. So say at a small open neighborhood of 0, you are evaluating all these functions and you get entire real number line. So x minus root 2 gets mapped to minus root 2. You are evaluating at 0 or in a small neighborhood of 0. So, and you have usual restriction maps. Yeah, so if a function is defined on a big set U, it is also defined on a smaller set V, which is contained inside U. Now you can do the similar thing with ring of differentiable functions or ring of holomorphic functions. So again, this example has been taken from Hartshorne, so you can start reading pages at the start of chapter 2. Now second example is, this is the most important example for algebraic geometry. So say X is a variety over a field K. Yeah, and U is a subset of X. So U is open subset of X. So O of U is ring of regular functions from U to K. So you have this map, this contravariant map. This we have already discussed before. And this is a sheaf of regular functions. Yeah, O is denoted as sheaf of regular functions on X. So this is very important. And therefore it gets a red star. So till now we covered the material just to have this example number 2. Yeah, so just the entire purpose of doing regular functions was to have example 2. So now we have an example of a pre-sheaf which is not a sheaf. So X is a topological space and A of U, where U is an open set of X, is just the integers. Yeah, U is open set of X contained in X. So restriction map is just the ID map on integers. So restriction map is ID map on integers. So this is not a sheaf in general. So let us show this why. You have these two sets. So we have these two sets, say U1 and U2, and their union consists of the entire space. You take a section -1 here and 1 here. Both -1 and 1 lie in integers. And you say the intersection of these two spaces is the null set, yeah, because these spaces do not intersect. So the corresponding element to the null set is 0. So -1 and 1 agree on the intersection, which is the null set, which is 0. Yeah, but the entire space consists of just these two sets, or the union of these two sets, say U1 and U2. So there is no, so we have to define an integer on the entire space which takes value both -1 and +1, because the entire space just consists of these two sets or these two circles. So there is nothing in integers which take values both +1 and -1. Therefore this pre-sheaf is not a sheaf. So we will resolve this problem later on, and we will fix this using sheafification, and we can fix it by two ways, by either saying that the space should be connected, or we will take something like z plus z. So the process to fix this is called sheafification, and we will cover that later. So now let us talk about stalks and germs. Yeah, this is very important. In fact, everything boils down finally to stalk and germ. Yeah, now stalk is a collection of germs. Yeah, so first we need to define a germ, and then bunch of these, you take these bunch of these germ and you get a stalk. So stalk consists of germs, and we first need to talk about what is a germ. So first I'm drawing the y-axis. So we draw the y-axis and we draw the x-axis. So let us draw some functions. Yeah, so this function is 0 at 0 and also in the neighborhood of 0. So this function is 0 at 0 and also 0 in the neighborhood of 0. And x-axis is 0 everywhere. Yeah, so that is clear. So x-axis and this function in rust color both are 0 at 0 and also in the neighborhood of 0. Now this function in green, it is 0 at 0 and 0 in the neighborhood of 0. Now this function in blue, this is just 0 at 0. It is not 0 in the neighborhood of 0. Now again a function I will draw in yellow. This is 0 at 0, but it is not 0 in the neighborhood of 0. So in the neighborhood of 0, this yellow function I just drawn is positive. So we need to decide which of these functions lie in the germ around 0. Yeah, around the origin. Now first notice that all functions take value 0 at 0. But not all of them lie in the germ. Yeah, not all of them lie in the germ whose value is 0. Yeah, so all these functions ticked in red are part of the germ at 0, but the functions which I have crossed out are not in the germ of 0. Yeah, the reason is that the functions which I have crossed out, they only become 0 precisely at 0, and the functions which are part of the germ, vanish or agree in a neighborhood of 0. So the neighborhood is very important. So there is a small tube around 0 on which all these functions which I have ticked vanish, and the functions I have crossed out, they do not vanish in this small neighborhood, and that is an important point. So germ, they make functions agree in a small neighborhood. Yeah, so not only at a point but small neighborhood. So for example, x equals to y and the x-axis both are 0 at 0, but both do not have the same germ at 0. Yeah, because x equals to y is only 0 at 0. It is not 0 in the immediate neighborhood of 0. So now you have large number of such germs. Yeah, so you identify functions together which agree, and then you construct a set of germs. Yeah, you take these germ and you construct a set. So not only at 0, so you have a germ at 0, but then you will also have germ at say -1, corresponding to functions which which take value equal to -1 in small neighborhood. Similarly, you have functions taking value 2, 1, 2, 3, root 3, root 5, so on. Yeah, so you will have, instead of just like we had a germ at 0, you would have a large number of germs all along the real line. Yeah, all along the y-axis. So all these germs now taken together form a stalk at origin. So this is how you get the stalk. So the stalk consists of all large number of germs. It consists of germ at 0, 1, -1, root 2, minus root 2, all real numbers, all rational numbers on the y-axis. So the stalk contains a large number of points. But first you need to understand how those germs come about. So now let us give a formal definition of it. So if f is a pre-sheaf on x, and if p is a point of x, we define stalk fp of f at p to be the direct limit of groups fu for all open sets U. So direct limit we are talking in the terms of category theory. For all open sets U which contain this point P. Via the restriction map. So we will just draw some figures and it will be clear. So you should be able to link this definition to the motivation just given above. So the point P above is 0, 0. So around point P there is a sequence of neighborhoods. Yes, a neighborhood say U1, U2, U3, U1 here, U2 here, U3 here. You have point P here. So corresponding to this kind of a figure, you have these maps, going in the opposite direction of inclusion. F of U3 morphism to F of U2, which goes into F of U1, and you end up slowly all the way to the stalk F of P. So you could also directly go from here to here. So the working definition is this. So Fp is represented by a pair. The stalk is represented by a pair. So pair consists of two things, U comma S. Now S is a section of the abelian group f of u or the ring f of u, and u is the neighborhood of the point P. So 2 points Vt and Us are the same if they agree on the intersection. So notice that Fp not only contains S, although it is represented by a pair U comma S, but a large number of sections. It is an entire abelian group. Yeah, just like I discussed in the example above. So if you're talking about point 0, then you're not only talking about functions which vanish at 0, you're also talking about all those functions which take value 1, minus 1, 2, 3, all real numbers. But they have to agree in the neighborhood. So let us first draw one function. Then we draw another function. So we have two functions, say s and t, and both agree on the neighborhood of P. So therefore they come in they define the same section. Yeah, but there are large number of sections.